Bismillahirrahmanirrahim. Today, inshallah, I'd like to talk about plasma membrane, a very important topic in biology. Plasma membrane, as you know, it's kind of like the fence of the cell. It's the boundary of the cell that demarcates where the cell begins or ends, so to speak. And just like a fence, it has a very similar purpose. It's to keep undesirable things from getting in and things from getting out. Like, you want puppies to go out, they might escape or etc. So the object is to allow things that are only meant to come in, and to disallow things that are not supposed to go. So it controls traffic both ways, and it has to have places of entry. In other words, of course, in the membrane, you have to allow certain things to come in. The thing about plasma membrane, however, is that it's like an underwater fence. It's surrounded by water, and inside the cell, the cytoplasm is also a water's jelly, so to speak. So it's a remarkable phenomenon if you think about it. It's like a fence that keeps things inside, that needs to be kept inside, but then it still allows things to come in and it allows things to exit. Okay, but and it has control over what comes in and what exits. So that's a very remarkable property of the membrane. It's called selective permeability. So this wall, this is not solid, okay, and it will not dissolve, although it's surrounded both sides by liquids, and it itself is a fluid structure, you will see. It will not dissolve, and it will have a selective permeability. Selective means it's picky. It's picky about what comes in and what goes out. Permeability is the ability for things to go through. So it has selective permeability, means it has the ability to control what goes in and out. So these are the remarkable features of the plasma membrane. So how is the cell able to accomplish this? The membrane, as you probably already know, is made of a lipid membrane. So it's made of lipids material, like oil. And you know that oil and water don't mix. So it is for this reason that the plasma membrane is able to separate itself out from its surroundings. And both the cytoplasm and the outside of the cell is predominantly water. So it's the fact that the membrane on both sides is essentially is surrounded by water is the ability that it's able to do what it does, because its natural inclination is to separate itself from water. If you can imagine a big droplet of oil, okay, and then if you can imagine that big droplet of oil being hollow, okay, that would be the membrane, and inside it would be filled with water, and the outside would be water. Okay, so that's the concept of a membrane. It's like a big oil droplet. It is empty, and it's a hollow oil droplet, like a basketball. It's empty on the inside, empty on the outside. It's surrounded on both sides by watery substances. But this membrane, however, is not a plain oil like this. It's made up of lipid material that have very special characteristics. And we shall study in a second. So the component of the building block of the membrane, the basic component of the membrane, is what's called a phospholipid. A phospholipid has two parts, okay? It has a hydrophilic head. This literally means water-loving, right? Water, hydrophilic, like loving, as in philosophy, right? We said before so many times. So hydrophilic means loving water, or this is a part that's able to interact with water. If you recall, water is a polar molecule. It has delta negative, delta positive charges, and this molecule, being charged, etc., is able to interact with water. So water molecules are able to interact with this side, and This side of the phospholipid, however, is hydrophobic, or fearing water. So this side of the phospholipid molecule over here does not like water. In other words, there's nowhere over here that is able to interact with either the positive or the negative negative part of water molecule. So this part is like pure oil. If you were to take all these phospholipids and just put them in a glass of water, you would get exactly like that. Okay, you would get this. It is the two-part aspect of the phospholipid head and this hydrophobic tail, the hydrophilic head and the hydrophobic tail. It is this double nature of this particular molecule that allows it to form this bilayer. It's like a sandwich, right? It's like a little sandwich. And if you recall, both the hydrophilic part, the water-loving part, so to speak, over here, the water-loving part, they're faced on this side, and they're faced on this side. And that makes sense because the outside and the inside are essentially water. Okay, and the hydrophobic part is what allows you to they face each other in this way, and then you make this sandwich of membrane. In fact, if you were to take a bunch of this phospholipids in a glass, and you shake them up like this, okay, they will naturally form membranes like this. They will naturally form tiny little micelles like this, or they'll form membrane. That's their natural thing to do. Okay, so what we learn here is that the particular nature of a cell membrane is because of this property of a phospholipid. It has two parts to it: a hydrophilic head and a hydrophobic tail, and that you must appreciate. So it's the phospholipids properties of being the hydrophilic head and hydrophobic tail. It is what allows you to construct this membrane. If you were to throw phospholipids in a cup of water, they automatically will form structures like this. Either they would do something like this, because again, the water would be all around it, and the hydrophilic part would be naturally facing outside, and the hydrophobic part would be facing inside. Or you would do this, or you would do this. In a cell membrane, it does this. Now the structure of a cell membrane is just not like this. It's not like floating like this, right? The cytoskeleton is going to is taper, like it'll be like a glue that's going to hold all of this together. But the basic structure of a membrane is what is described over here. It's called a phospholipid bilayer. Bilayer meaning two layers. In other words, two layers of phospholipids. So how would you describe a plasma membrane? A plasma membrane is a phospholipid bilayer. It's two layers of phospholipid, with both the hydrophilic ends facing on the outside and the hydrophobic ends facing inward. Now over here what you see is a more realistic depiction of what a phospholipid looks like. It has a polar head group, meaning it's able to interact with water, okay, and it has these long fatty acid chains on this side. Fatty acid, if you recall, is just long chain of hydrocarbons like this, okay, and then you take two of these over here like that, okay, and you hook them up at the glycerol molecule over here, okay, like this, and then over here you have a phosphate group, hence phospholipid over here, and it is this part that interacts with water, and this is the hydrophobic part. Now, if you were to attach, by the way, which we're not going to do over here, but if hypothetically, if you were to attach another over here, that would be like a triglyceride type structure. Triglycerides is just three fatty acids attached to the same molecule of glycerol. That was a slight digression that was not meant to confuse you, but this is the structure of a phospholipid. It has two fatty acid chains attached to this glycerol molecule, and over here is a phosphate group. This is the polar heads of the phospholipid. This is a three-dimensional rendition of the molecules. Here again is the hydrophilic phosphate head groups, okay, and in the middle are the two hydrophobic parts of the phospholipid membrane. Okay, and then you can see on both sides you'll see water. Now, if you were to elaborate on that, the first thing that you said is the membrane is a phospholipid bilayer. That's the first thing that you said. Okay, and the model that describes the plasma membrane is what's called the fluid mosaic model. Okay, well, fluid mosaic model. Let me try to do this at least for God's sake one time. That's proper. Okay, so fluid mosaic model. So, in other words, the plasma membrane is a fluid structure. That is, it's not like cement. Okay, so it's not like a hard thing. It's not like bone. It's fluid. It's flexible. Okay, so as you can see in this over here, it's kind of moving. So it has this ability to allow things to move around it. This is quite remarkable. So it is fluid. And then it's a mosaic. Mosaic means, in common parlance, mosaic means if somebody takes all the family pictures and picks out some collection from the family pictures from all the years, and then makes one big picture with all the different pictures, that's a mosaic of family pictures. In other words, different things studied in one area. So it's a fluid. In the plasma membrane, a lot of proteins, sugars, and cholesterol are studied. They're like gems in the membrane, and that's the mosaic part. It is fluid mosaic and has different things in it. So it's a fluid mosaic model of the plasma membrane, which is composed of phospholipid bilayer. So here's the plasma membrane depiction, and here is the protein that goes across, that's studied in there. Okay, there are many different things that are studied across the plasma membrane. There are receptors over here depicted. Okay, and they're channel proteins, which we'll talk about. They're gated channel proteins. There's proteins that have carbohydrates attached on top of them, and there is cholesterol. The cholesterol that has a bad reputation, in fact, is very important for the integrity of the plasma membrane. It gives stability to the plasma membrane, and if it were not there, plasma membrane would not be what it is. So the fluid mosaic model of the plasma membrane is this. Okay. And this was apparently proposed by Jonathan Singer and Garth Nicholson in 1972, the fluid mosaic model. These are like key words that you kind of have to know. It's like you can't go through biology and not knowing that the plasma membrane is made of phospholipid bilayer, and the model that describes is the fluid mosaic model. Here are some other very beautiful depictions of the same. Okay. So these are some proteins that are studied in the plasma membrane. You can see how the fluid nature of the plasma membrane over here. In fact, proteins can move around in the plasma membrane carrying things, and there are transports in the proteins that allow things to go in and out, just like the gates in a fence. So here's some things going in and out through channels that are in the membrane. The channels are invariably made of proteins. These are big protein molecules. They're like gates in the membrane, and there are different types of channels. Some channels need energy to function. That's what this is trying to describe over here. This last channel, see, is requiring energy for it to function. The other two channels are not requiring energy to function. That's what that's trying to depict over there. Okay. So when does a transport need energy and when does it not need energy? Okay, we will talk about that in the future, inshallah. I'll let you think. So the first, and now we understand how the plasma membrane is able to separate two compartments of water, right? Water on the outside, water on the inside. The second aspect of the plasma membrane, if you recall, it is selective permeability. In other words, it's very picky for what it allows to come in and out. One things that cannot get across are charged molecules and ions. Any ion, however small they may be, Any ion like sodium chloride. That's very important because they would kill the cell possibly. So any ions, they are not able to get through. Okay, they're not able to get through the membrane. Any charged molecule, for that matter, whether it be big or small, are not able to get. So any charged molecules, they are not going to be allowed to get through. Okay, so charged molecules, ions, can't go through. Small molecules that are not charged, like water, ta-da, in and out at free will. Okay, so water has no trouble going in and out of the membrane. Also, other non-charged small molecules. So small non-charged molecules can get in, just like water can. So water is basically a non-charged molecule anyway, right? So non-charged small molecules can get across. Ions, no. Okay. Now, big molecules like macromolecules, like proteins, etc., they can't get across. Okay. So they have to, if the cell wants it, has to make some effort. So they no in and out except. Okay. So the big picture here is charged stuff, no. Small non-charged stuff, okay. Big stuff, no. So here's a summary again. So small molecules, okay, especially if they're hydrophobic molecules, are easy peasy in and out. That's very important because oxygen, every cell needs oxygen, right? So oxygen can get through. Oxygen gets into cells by simple diffusion. Carbon dioxide leaves the cell. That's a waste product, and you breathe it out. Carbon dioxide leaves the cell also by diffusion. There's no special transport for these molecules, and same thing as nitrogen. And small molecules like water are able to get in. But bigger molecules like sugar, okay, they can't get in. And ions, as we said, they can't get in at all. Okay? Now, here's a visual depiction of the same. These tiny thingies are water molecules, and these are some other bigger molecules, and you'll see readily that the water molecule is able to get through, and the green thingies are not able to get through. Now, in this depiction also, excuse me, you notice something interesting. The water is going to go from here to here. Okay, the reason it goes from here to here is because of the concentration gradient. Water itself has a concentration gradient. Wherever there's more water, and the water moves from wherever there's more water to wherever there's less water across its own concentration gradient. Now you can observe that here again. See? So things move always in the direction of the naturally things will move from higher concentration to lower concentration. Now water is able to get through over here, okay, by itself, but that's a slow process. Let's see if the cell wants lots of water all of a sudden, or cell wants to get rid of lots of water for all of a sudden. Okay, so the cells actually have special gates, so special charges that allow water to open, allow water to go through. For this is, you can find this in the kidneys, for example. In kidney, we pee out water a lot of time, and they have special channels just for water. So if it really wants to gain water or lose water, there's special protein channels that allow or facilitate water to get across. Okay. Now, other things that the cell needs that are unable otherwise to get through. Okay, for example, if there are like glucose molecule over here, we said already that the glucose molecule cannot just get across the membrane. So therefore, it must have a channel. So here's a particular glucose channel that you will see. I think that's what they're trying to show. There are membrane proteins that are called channels or gates, which allow the glucose to come in like this. You also notice that these channels are specific. The glucose channel did not go through this membrane protein, but it went for its own specific channel. So specific things have their specific channels. It's a small non-charged molecule that's getting across over there. So there are membrane proteins, which are called channels, which allow stuff to get in, and there are specific channels for specific things. Now these channels have gates of themselves, just like the gate of a fence. There's no point if it's always open, right? So it's closed, and when the cell wants it, the cell can open it. The cell can open the gate to allow it. Now this occurs with different things. and especially with ions. If the cell wants certain ions, it will open the gate for that ion so the ion can get through. So the gates will be closed and open on the cell's volition. If the cell wants it to be closed, it will be closed. If it wants to be open, it will be open. Now, here's an interesting phenomenon. If you observe here, something very interesting is happening, okay? Now, we said that things will go from area of higher concentration to area of low concentration, right? So things will naturally go from area of higher concentration to area of lower concentration. Now, what if you wanted to move things from area of low concentration to area of high concentration, right? That's not the natural disposition of things to go. So when you try to move things from area of low concentration to area of high concentration, okay, that is going to require energy. So that is going to require energy. The process of moving things from low concentration to high concentration will require energy. And energy in the cell is in the form of ATP. So ATP energy is used to move things from low concentration to high concentration, and in the process ATP is changed into its non-energized form, ADP. Okay, this is adenosine triphosphate. It stores the energy for the cell. It's like the cash for the cell. When it's used up, it's called adenosine diphosphate. Okay, so now this example, what you're seeing here, you see there's a lot of green over here, right? So this cell wants the green to go out against its concentration gradient, and it wants this yellow to come in against its concentration gradient. You see this? So it wants the green to go out like this, and it wants the yellow to come in both against the concentration gradient. For this to happen, you must understand the cell is going to have to shell out some cash. The cell is going to have to spend some energy, and that energy is going to come in the form of ATP, as you will see over here. So now these are ions. Ions, first of all, are not going to go to the membrane on themselves, so they're going to need help to begin with. And these are not, and these are ions that are going against concentration gradient. Now what you see over here is actually one of the most famous membrane channels of all. Really, I'm not kidding. It's one of the most famous membrane channels of all. This is called the sodium potassium ATP using ATPase. That's what this got a name actually. It's called sodium potassium ATPase channel. It allows sodium to go in one direction, and it allows potassium to go in the other direction. This channel, for example, is what allows you for nerves to transmit electricity across their nerve fiber across the axons. This is one of the most famous of all protein transports. Okay, watch what happens here. Okay, look, there we go. Sodium is going out, potassium is going in. Sodium is going out, potassium is going to come in. Okay, now interesting, this channel is intelligent channel. Okay, it's very intelligent, efficient. What do I mean by that? See, what happens is when sodium, potassium goes in over here and then goes and attaches to the protein, the very fact of the potassium attaching to the protein causes the protein to change shape. And when that happens, it causes the protein to change shape. And when the protein changes shape, the shape changes in a way that the potassium no longer desires to be with the protein because of the surrounding electrical activity, so to speak. And then it's kicked out. And that process opens up these channels, these spots for sodium to come in and sit over there, which causes another conformational change. So potassium is going to sit over here, and as you're going to come in, there's going to be a change in the shape of the protein, allowing the potassium to leave, and then which opens up this 3 spots over here for sodium to come and sit, and then another change will occur. So it's really quite a remarkable phenomenon over here, if you can observe and see. It was the other way, I'm sorry. Okay. But you get the idea. It's very, very beautiful how this occurs. Okay. So now we're still talking about the channels in the membrane. So some molecules, the tiny ones, are just able to get through. And there's some transporters that allow certain things to go through directly. So some channels are called facilitated diffusion channels. In other words, there's lots of the stuff over here and there's a little bit of it here. So it wants to go this way. The channel just facilitates that diffusion. Okay, that's called facilitated diffusion. Okay, so some of the times these are very specific for certain molecules, and they're like over here. It's a very specific facilitated diffusion. So this is facilitated diffusion of glucose. Means there's lots of glucose over here, and this channel is just going to help the glucose come across. And we talked about specific water channels, and here's aquaporin, for example. It's a channel for water. So here's a complete picture, a cartoon picture of a plasma membrane with various different proteins and protein channels embedded in the membrane. Now, many proteins, in addition to just channeling across here, you notice they kind of have these antennas. These antennas are typically made of glycoproteins. They're not just there for decoration, okay? Obviously, they're there because they are an integral part to the function. They're integral to the function of the protein. Sometimes these glycoproteins they give a unique characteristic for the receptors of the cell, etc. So they are integrally related to the function of the protein, the carbohydrate part of it. And what you see in this cartoon picture is all this filamentous network. It's like little threads of filamentous network, which kind of gives some stability to the membrane. Yeah, and they also allow things to move across the membrane. Things kind of move on a membrane by tugging along on these on the cytoskeleton, filamentous cytoskeleton of the cell. They are highways for the cell. So that's a brief survey of the plasma membrane, and next time we shall go on to talk about the eukaryotic cell structure in more detail. Until then, assalamu alaikum.